Okay, I think it is recorded. So let's begin our talk on the new method. It's called the approximation. Approximation, analysis, or method. Okay, actually, this is a very useful idea, and it's not that difficult to do. The approximation analysis requires quite a good few assumptions, and this is predominantly for prelim design, for preliminary design. Now, it may not give you the accurate results, just like the slope, deflection, or moment distribution, but it is very good when you want to know the size of your structure from the beginning, see if the configuration you choose for your frame will work or not, and stuff like that. Okay, so oh, I cannot read my handwriting, so let me put this here. I don't have the lecture for, I don't have the handout for this one because it's been added only a few years ago. So it's a prelim design for economy. Okay. And it can also, you know, be used to check on complex problems. Okay. All right. So we need to have some assumption on it. Additional equations must be supplemented to eliminate redundance using what we call engineering judgment. Okay. So what we do is we are going to assume locations of, can you guess, the point of inflection, because I always mention that the point of inflection is the point where the curvature of the moment changes from negative to positive or vice versa. So before the curvature changes, before the moment changes the value from negative to positive or vice versa, it has to become zero first. Now, zero is a fascinating number because if it was invented long after the integers, you should know that. So if you go back and take a look at the very old languages, such as Chinese and Japanese, they don't have the word zero from the beginning. And they just add that later on. For example, Japanese would have their own words for 1, 2, 3, 4, 5. You guys should know that. But when it comes down to the word zero, they just use zero. You know, there's no Japanese word for zero. They use zero. Okay. So people only realize later on, you know, that they need the number zero to divide the positive and negative numbers. So the zero is an important point because at least that's the point where we know the value of the moment, which is zero. Okay. And therefore, if you're dealing with the structure that has redundance, it's safe to say that number of you know, point of inflection or hinges should be pretty much equivalent to the number of redundants that you have. Okay, and one more thing, you can't just put the point of inflection or the assumed location of the hinge anywhere you want. It has to be locations must be selected to give you a safe structure as well. Okay, so let's say, for example, if we are dealing with a beam with both fixed support like this, yes, you can easily calculate the fixed end moment and stuff, right? And your bending moment diagram will look like this. Okay, I should give the load. Okay, and if you can draw the deflected shape of the structure, this is a fixed, so it is 0 here. This is fixed, so it's 0 here. So the picture of the deflected shape should, you know, have a relationship with where the hinge is, where the hinges are, right? So generally, they say this point is roughly like 0.2 L. Okay, so let's say if you have a structure like this and you put the point of inflection on it, or you put the internal hinge on it like that, it becomes a determinate structure. Correct? Because if you have the load, you now can divide your structure into a cantilever beam with your another simple beam on it and another cantilever beam. So you can solve that. Okay? Because let's say how many you have? 1, 2, 3, 4, 5, 6 unknowns. You have 3 equations, so that's 3 degree of redundancy. You add 2 hinges, and then you ignore your sigma fx equal to 0. You ignore your axial force. You're fine. Okay, so by doing that, you can easily solve the indeterminate structure just by adding the hinges to the locations where they should be. Now, generally, it's at the point 2, but in terms of approximation, they would say whenever you have the structure, the continuous beam, the location that you should add the hinge should be about 10% of the length, just to be safe. Okay, and we are talking about the vertical load now. Okay, so it's the same if, let's say, if you have a frame, okay, that takes care of only the vertical load. Now this frame has 1, 2, 3, 4, 5, 6, 7, 8, 9. So you have 9 plus 3, that's a 6 degree of redundancy. Okay, now if you add 4 hinges, just like on top, you eliminate 4 redundants, and you have to ignore 2 more axial forces. You can solve this. Okay. Now that's it for the vertical load. It should not be too much of a problem, and I don't see why we are going to analyze the frame if we have only the vertical load. You can just decide analyze it as a beam like this, and by adding the hinges at the location 10% of the length, you should be able to solve it approximately, you know. Okay, so now let's move on to the more fun thing, that is for the lateral load. Okay, for the lateral load, let's skip to the next page. For the lateral load, we have 2 major methods of approximation. The first one is called the portal method. Portal means a door. Okay, and we look at the frame, the structural frame like the frame of a door. Okay, I cannot see his name very well, but I think his name is A. Smith, who was an engineer who developed the portal method in 1915. Okay, so now before I talk about the portal method, I should try to emphasize the fact that when you have a frame, okay, let's say for those of you who have practiced enough of the bending moment diagram, when you have the frame and you push it to the side, you should be able to guess by now that this is 0, right? So your frame will sway like that. Your frame will sway like that, and your frame will sway like that. Okay? So because this is the rigid joint right here, this is the rigid joint, this is the rigid joint, and this is the rigid joint. So when the column starts to bend like this, you know, when the column starts to, oops, I don't want that one. So I gotta do it again. When column starts to bend like that, this angle is no longer 0. So it has to rotate. And this too. And to maintain the rigidity, that should be your, you know, the line that parallels to the joint. So this member, it should go like this. And then this member should go like this. And so this should be, you know, confirmed by your bending moment diagram. Okay, so that means we can assume that the hinge should be somewhere in the middle. Here, 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 and here. Okay, so when we go back to look at the typical frame, okay, that means I can start the approximation by simply adding the internal hinges to these locations. Right there in the middle, you know, it may not be just right in the middle like all the time, because you have, if you have done your work from, you know, the sessions, you probably realize that it may be a little bit off. So this is the approximation. We know that we're not going to get the exact answer, but it is good enough in many cases. So we can apply the hinge to exactly at the midspan of each member. Okay, but you should know that Okay, let me summarize by step number 1 is hinges are in the middle. Okay, but you see, this is not enough yet to solve the structure. Okay, because you see that you have 9 reactions here. 1, 2, 3, 4, 5, 6, 7, 8, 9, and that means you have 6 degrees of redundancy. You just add 5 hinges, so one more thing is needed. That is this. Because this is the Porter method, so we are going to assume that the each column will take the equal shear, and the ones in the middle, like this one, can be split into 2 columns in a manner that you have, like if this is a 2-bay frame, you would have 2 doors. Okay, that's one door, that's another. So you just split the column in the middle, you know, into 2 columns so that you can have 2 doors. And then each of this will take equal shear, which means that this one will take V. This one has 2 door frames, so it becomes 2V. And that one is V. So, you know, after we make this assumption, you can go ahead and start the approximation of your structure right away. Say internal frame can be split and therefore interior columns, they're basically equal to 2 exterior columns. Okay, that is the Porter method. Okay, it is, I should write here, appropriate. This is appropriate for low building frame. Okay, the next one, if your building gets taller and taller and taller, we can use this one that is called the Cantilever method. This is done by the guy called A.C. Wilson in 1908. Okay, so basically, you know, again, let's say if you have a frame, this time I'm going to draw it a little bit crooked so that you have a feeling going on. Okay, this guy say you can say, actually say, so you see, it should have passed away some time ago. Okay, you can look at the behavior of the frame as a cantilever beam. So if I flip this 90 degree, say if I flip this 90 degree, you would see picture like this instead, right? Should be straight line here. Like that instead. So with this method, you look at your frame as a flexural member. So that means if you look at this, say, if you look at this as a beam, this will be your neutral axis. Okay, and therefore, with this method, you know, you should notice that the first method you obtain the base shear, but with this method, you know, when you look at the frame as a beam, a cantilever beam, you will see you will have the bending stress distribution like this, and you can use the ratio based on the distance measured from the neutral axis to calculate this time the force in your columns. So let me try to come back here, and let's say I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 blocks. So this becomes my neutral axis, right? And I can now calculate the forces in the columns based on this ratio. Okay, so you see this force will be compression based on this distance. This force in this will be slightly a compression, and here that will be tension. So, okay, that's a cantilever method. And to do this, generally, in order to use this relationship to calculate, again, hinges are in the middle as usual. Same, you know. So it should be here as usual. But for this method, axial forces in columns are calculated first. Okay? By distributing forces in accordance with the cantilever beam what should I say, anomaly, like this. Okay, and of course, if the first method is appropriate for low building frame, this is, you know, appropriate for relatively tall. That's tall, okay. Ooh, difficult. Looks like fall. Tall building. Okay. Well, this is not to say that there are only two ways to approximate the structure, and that only, you know, for tall buildings, there are only frame structures you should form. There are more than one type of structures that engineers use for high-rise building. For example, the concept of a tube, the outrigger structure, the combination of the frame and cantilever beam, and so on and so. But this is the basic that you guys should try to understand. Okay, and we can use this concept to approximate all the internal forces in your frame. Okay, is there any question? Because there's no more to do than to try to go through the example, which we will start in the next session. So I think you guys can have a break now after a slight surprise from your midterm results. Make up your mind, and if you decide to carry on with the class, come back with the absolute conviction that you really want to do it. Okay, so is there any question?
Teacher, can I ask some question?
Yeah.
For V and 2V, so I cannot understand. You can
Sure. Okay.
explain.
I gotcha. I gotcha. Okay. So let me redraw this again. Okay. You are talking about this picture, right? So on the portal method, we would say that we have doors. We have a space here, like this one, you know. So I can draw the frame like this one as like two doors, like this. Okay. So with the columns in the middle, you know, because this is interior column, so it's equal to two exterior columns. So right now, you know, you have, let's say 4 columns, right? 1, 2, 3, and 4. And then you have the external forces. You have 4 columns to deal with. So basically, it's this. If this is P, this V is equal to P over 4 because you have 4 columns to deal with. So you divide the external force by the number of columns you have, which is 4. And then this is 2, so this becomes like 2 V's because you have 2 columns. And then this becomes just 1 column, so it's 1 V. So this is P over 2. And then this V is P over 4. So in the end, it's P and then that's P. So let's say if I have like this. Okay, if I have now 4 columns. Now, how many do I have? I have 2 exteriors and then 2 interior columns, right? So that means I would have a V here, and then that's 2V, that's 2V, and then that's another V. So in total, I have 6V that would be equal to 1P. This V will become P over 6. That's 2 V's because I have 2 columns tied together. That's P over 3, that's P over 3, and then that's P over 6. That's simple, you know?
Oh, yeah. Thank you, teacher.
Okay, sure. And there's no surprise that, you know, everyone should do well in the approximation method. And, you know, there's a slight argument amongst instructors, a slight argument because only a handful would know how to deal with this. But I believe Ajahn Ekachai teaches this in the regular program as well. And I used to talk with Ajahn Anek and he made us some small suggestion that maybe we should teach this first. We should teach students to approximate the structure first, and then you teach the slope deflection or moment distribution later on for a more precise or more accurate calculation. But I don't know, because things like this, there's no right or wrong, you know. But I would rather teach this later because if you know you can approximate things like this, you probably do worse with the slope deflection and moment distribution, which give you more accurate results. You know, this has limitations. Let's say because in order for us to do something like this, you know, that means we assume the stiffness of the, doesn't matter, columns and beams, right? We simply ignore the stiffness for the time being because this is the approximation, like I have stated before, that this is used to either check the prelim design, to design on how many columns you're going to have and stuff like that, or to check the complex calculation. It should give you say good approximation, but it will not work very well at all if you do some strange stuff, like for example with the stiffness. So it is always important to understand slope deflection. Okay, good question that is. All right, any more questions? I'm glad that the record is still on, so that the answer to that question is recorded. So the sharing is gone. I better stop this, and I'm going to stop the record.